Assalamualaikum warahmatullahi ta'ala wabarakatuh. Welcome to another video on MCTE 2311 Signal and System Analysis. In this video, I will show you the solution to problem number 3 on modeling of mechanical system. Where in this figure, you are given a mechanical system with rotational motion. So you have here the J1, which is referring to inertia. So inertia 1, inertia 2, with rotational motion of angular displacement theta 1 and theta 2. So this capital T of T is the input torque. Okay, so these two inertias are connected by this spring with the spring constant of K. So to determine the differential equation that represent this system, we have to solve for individual mass. Okay. So let's start with J1. So for J1, if we draw the free body diagram, I like to draw with respect to the surface here, okay, because I find it easier to draw the input torque as well as the reaction torques. So if I draw that, let me just draw it over here. If this is J1 with rotational motion of theta 1 of T, okay, it has an input torque of capital T of T. Now the reaction torques will be torques due to the inertia J1, the damper B1, as well as the spring K. So we can refer to the slide that I provide to you and I discuss in one of the videos as well. This is the relationship between this one supposed to be torque to displacement relationship, angular displacement. So you have here for the spring, the damper, and the inertia. So if we substitute this into our free body diagram, we'll have one is reaction torques due to J1 given by J1 multiplied with the second derivative of the angular displacement. Next we have torque. This one is wrong because the reaction torque direction is similar to reaction forces. In the linear mechanical system, the direction must be opposite to direction of motion. Okay, so the arrow here goes up instead of go down. Next we have reaction torque due to this damper B1, which is multiplied with the first derivative of the angular displacement. And lastly, we have torque due to K. And the K here is connected in between two rotating masses. So we have here theta 1 minus theta 2. If I write the equation of motion to represent the differential equation for this J1, so it will be J1 d square theta 1 t over dt square plus b1 t theta 1 t over dt plus k theta 1 of t minus theta 2. This one equals to the input torque. Okay. So let's call this equation number 1, which is the differential equation for the first mass. Next, if I draw the second mass, which is J1, J2, I have the angular displacement theta 2. This time there's no input torque, so I will have the reaction torques 1 due to the inertia. Another reaction torque due to the damper. And reaction torque due to K. This time we are modeling J2. So we will have theta 2 minus theta 1. So if I write the differential equation, it will be J2 plus K. This one is theta 2 minus theta 1. This time is equals to 0 because no input torque applied to J2. So we have here equation 1 and equation 2 that represents the differential equation for the given rotational mechanical system. Thank you for watching this video.